Whenever you're ready, Vera.
Okay, welcome everyone. My name is Vera Koster, and together with Diederik, Bauli, and Vasoka, Georgina, and Alex, we have designed Clotho. In this presentation, we will explain to you our design process, then present to you our final product, and we'll conclude with an experiment setup to test our design. The inspiration for the name of our project comes from ancient Greek mythology. Clotho is one of the three fates that spins the thread of life. In order to keep Clotho spinning in modern society, we have to switch to renewable energy sources as soon as possible. One of the challenges in switching to renewable energy is making it accessible. If you look outside, you will see a vast amount of unused building surfaces, perfectly suited for solar energy generation. The only problem is the variety of building surfaces. Everyone in our team came to the same conclusion. In order to apply photovoltaics to all these different kinds of surfaces, we need something flexible. This brought us to our concept of a solar fabric. The criteria that we continuously measured our design to is robustness, lightweight, efficiency, and how easy it is to install. Our design process can be divided in two main stages, each stage containing important realizations. The first one is that a fabric isn't the only solution to create something flexible. Rigid PV cells like polymonocrystalline have a higher efficiency than flexible PV cells like thin film. This led us to our decision to place rigid PV cells on a flexible back structure, a mesh. Our second major realization came when we said to ourselves, who asked? Who asked for a robust but lightweight, flexible but still highly efficient solar fabric? After all, most building surfaces are straight. So again, who asked? Space architects. We're going to Mars. This of course brings its own challenges, so let me explain some of the condition differences on Mars and Earth. The atmosphere of Mars is about 1% on the atmosphere of Earth, causing large differences in atmospheric pressure and harmful cosmic rays. Besides that, we also have to deal with extreme temperature differences and dust storms lasting over a month. Luckily for us, AI Space Factory already designed a 3D printed habitat on Mars that will protect us from this harsh environment. The fact that it is printed by robots gave us some limitations in shape, size, weight, and assembly movements, which we explored during the building weeks. So we already established that our final product is a flexible mesh with rigid PV cells. But since ordering spare parts from Earth isn't really a thing on Mars, we decided to make every PV cell individually replaceable. But how exactly does this work? Our flexible PV panel consists of two main elements, the mesh and the PV cell. The vertical cable of the mesh carries the weight of the cell and contains the electrical wiring. The diagonal cables provide the panel its flexibility. The panel is 2.4 by 1.4 meters or 12 by 8 cells. On the point where the cables cross, a circular connection board can be found. A row of cells is connected in series, and these rows are then connected in parallel. This way, when we replace the cell, only part of the panel loses its function. The panels are fixed at the corners by two different types of pins. 3 pins to clamp the panel into the facade, and 1 pin with an internal junction box. We designed quite a few options for this connection, but haven't been able to explore it to its fullest since our building weeks were cut short. It's always nice to leave some room for improvement. The top of the PV cells are made of the highly efficient gallium arsenide, a material which is common for solar panels in space. You can see clearly that the cells only connect to the mesh when it's rotated in the correct position. One cell is 20 centimeters in diameter, so in a later stage, humans are able to replace a cell by hand. Between these cells, there's a gap of 1.5 centimeters to allow the hexagonal cells to rotate without having to remove a whole row. Main material of the PV cell is RFX1. That is a polyethylene modified by NASA to withstand the thermal stresses and the cosmic radiation. It's 2 times stronger than aluminium, but much easier to process. This material is used for the connection board and as well for the mesh. Since we have to consider the extraordinary way of transportation, the cell has been optimized for its weight. It becomes visible in the rib structure at the back of the cell. Speaking about transportation, let's take a look at how these panels will be produced and transported. Oh, sorry, I'm going to the end. Yes, for the first phase, the polyethylene elements will be produced through injection molding on Earth, and the complete panel will then be shipped to Mars. Meanwhile, robots are busy printing Marsha, leaving 1 extrusion per panel for the junction box. When the structure has dried, 3 more holes will be drilled in the facade. Then the robots will wrap Clotho around Marsha. Our product has an approximate lifespan of 10 to 15 years due to the harsh Martian environment. But if an element breaks, spare parts can be printed on Mars. No need for as long interplanetary delivery times. So, over a couple of years, this will be the view on Mars. Clotho provides every possibility to transform Mars into a livable, pleasant place to be. As I have mentioned before, dust storms are quite common on Mars. You can probably imagine the potential loss of efficiency. To validate some of our design decisions, like shape and anti-dust coating, we will test our panels for dust accumulation by recreating the Martian soil. We do this by the use of an electrostatic chamber or the ISS, the International Space Station. After the chamber conditions, the first step is to prepare the mixture, so to recreate the Martian soil. And after the chamber conditions are set, the instruments to simulate a dust storm will be positioned. The instruments we use is a sandblasting gun, and we take a picture of it every 10 minutes. These pictures will be run through analyzing software specifically developed to measure the dust. The total test duration will be 2 hours, since this is the limitation of the electrostatic chamber. As usual for scientific research, the test will be repeated at least 5 times. The results of the test will hopefully validate our design decisions in terms of geometry and used coatings. It will take a few years before Clotho can be realized on Mars, but luckily there are some good alternatives on Earth. Clotho is a solar fabric that you can wrap around any building on Earth to make it energy efficient. And since we won't have to deal with the harsh Martian environment, the lifespan of the panel will drastically improve. Thank you for letting us share your product with you. We hope you enjoyed our time as much as we did.